discrete optimization before last lecture on constraint programming. Okay, so one of the things that I told you at the beginning is that there are two aspects which are really critical in a constraint programming system. One of them is constraint propagation, and we spent a lot of time looking at that in the past lectures. And what the other one is search, and that's what we're going to talk about in the next two lectures. It's also a very active area of research, and therefore what I'm going to talk about today is basically an introduction to some of the concept. Basic introduction, once again, to make you curious, right? So the key idea in constraint programming is that search is based on feasibility information. Okay, so what the constraint programming system is doing very well is basically pruning the search space based on constraints and feasibility, making sure that as many of these constraints are feasible. And the search, of course, is going to exploit that information because that's the big information that we have in a constraint programming system. Okay, so what does it mean to exploit this feasibility information? So we have this very high-level principle that we want to apply, which is called the first fail principle. And it's very counterintuitive, but actually it makes a lot of sense. So what you are trying to do, so the principle tells you, try first where you are the most likely to fail. Okay? So and the way to think about this is that you have a bunch of tasks that you have to accomplish, and you get a reward if you accomplish them all. And one of them is really hard. Don't postpone it. Focus on it. Because the easy stuff, you can do the easy stuff, but you're wasting your time if you can't do the hard stuff. That's what this principle is telling you. Try first, where it's when you are the most likely to fail, because you want to fail early. Okay? And so essentially what it means is that you don't want to spend time doing the early stuff and then go to the tough stuff and see that, no, I can't do the tough stuff. Go back and try to do the easy stuff in another way, such that in the hope that the hard stuff is going to be a little bit easier. That's not what we want to do. Okay? We want to start with the hard stuff as quickly as possible. And of course, by starting with the hard stuff, what we hope is that we'll have a very small search tree and that the easy stuff we can take care of at the end. So that's the first fail principle. You want to start first where you are the most likely to fail. Okay? Now, what does it mean? Well, look at this beautiful Queen's example that we have. Okay? So what does it mean to look at something which is tough, where you are most likely to fail? Okay? Now, all these queens, they have different set of values. Okay? And what you want to do is to start with one which has as few values as possible. This one has only one value. You know that you have to place the queens there. Okay? Now, if there are some values which have, some queens that have 4 values and some which have 2, you want to start with the one which have only 2 values. They are harder to place, and that's where you want to start for. They are also constructing a smaller search space because now you have only a branching, factor of 2 instead of 4. Okay? Now, sometimes all the variables have the same set of values at the beginning. Okay? So this is what we see in this particular graph coloring example. At the beginning, I can use all the colors for actually all these countries, right? And so which one do I start first? Okay? Now I can say, I'm going to start with Denmark. Okay? But Denmark, in this particular case, is easy, right? So it only connected to Germany. So there is only one color that it won't be able to take. And therefore, I don't want to start there because I'm going to give it a color that's going to remove a color from Germany. But that doesn't mean anything, right? So what I have to start from is some place which is essentially connected to many different countries. And that's where it's going to be the most difficult to color. In this particular case, guess which country it is, right? So we'll start with Belgium, okay, for instance. Okay, so I want to illustrate also the first fail principle on a very interesting example. It's a puzzle, okay? It's called the Euler Knight problem, okay? It's basically having a knight in chess and making sure that you visit all the places in the chessboard and visit them exactly once, okay, following the rules of chess, okay? Now, it's pretty tough to do that manually. I know only one girl who actually did that. She was in a computer science class, computer architecture. She was completely bored, and so she was playing this thing during class. And at some point, she said, yeah, and she found it, okay? So if you can't sleep at night, try this. It's not easy, okay? Now, it's an interesting problem because it's connected to a lot of problems in routing. It's kind of an abstraction for these problems, okay? So, but essentially, what I want to show you is the first principle on this particular example because it's very intriguing, okay? So this is the model. You see a very simple model for this. The decision variables are the jump variable, okay? Basically, for every position in the chessboard, okay, you have to know where the knight is going to jump next, okay? And so you have basically 64 variables, one for every position in the chessboard, and that tells you where you jump next. Once you have those, you can follow the path of the knight. Okay? And the only constraint that you have is that all these variables have to make up a circuit. Okay? So if you start from one place and follow this path, you're going to go back to exactly the same place. Okay? And you will visit every position in the chessboard exactly once. Okay? Now this is a tough constraint to implement. You can just think about it, and we'll come back to that later on. Okay? But this is essentially how the model is stated here. Now, one more thing that we have to do is we have to know, basically specify for every position where the knight can jump. That follows, basically the rule of chess, and this is this boring, set of positions that you see over there. Don't try to spend your time understanding it, but you just have to know that this can be done. Okay? Now, what I want to show you is essentially how the first veil principle is working on this particular example. Okay? So let's look at the chessboard. This is the chessboard at the beginning. Okay? So where do we start? Okay? Are we starting at the middle? Are we starting here? Are we starting over there? Okay? Well, the first principle is telling you start first where you are the most likely to fail. Where are the positions where it's difficult to actually, jump? Okay, well, these are the corners, right? So when you look at this guy here, okay, there are only two positions where it can jump, and as soon as it jumps to one, okay, you know that where the previous, where essentially the previous position was. Okay, so essentially there are only two positions, and as soon as you choose one, you also fix the value of another variables. Okay, that's where you're going to start. These corners are tough because there are only two places where they can jump. If you're in the middle, there are these 8 places where you can jump, many more positions. Okay, so we know where to start. Okay, so the key question here is where do we go next? Okay, and every time I've been teaching a class on combinatorial optimization and ask this question, people always tell me, okay, well, you have to take this guy probably because it has very few positions. Okay, but this is not what the system is going to do. Once again, the system is going to look at all the positions and find out the one which is the toughest to assign. And where is that? Well, that's another corner. Okay? Because once again, there are only two positions. Well, for this guy, there are at least 3 or 4 positions. 4 for that particular one. Okay? So essentially, what the system is going to do is build some small paths all over the places. And the constraints is essentially trying to make sure that you can connect them into a big circuit, okay, at every stage, after every assignment. So this is a partial state of the system. You see, we built a couple of interesting paths all over the place, okay? And this is a solution at the end, okay? Beautiful, right? And so this is what the first field principle is actually doing on the Euler Knight problem. Finding the variables which are the toughest to assign. They have a small domain. That means that they are tough to assign. Okay? So let's put this principle in perspective now, and let's look at how you program this search and how you can express them. Okay? So I'm going to start with the 8 queens problems again, such that I can illustrate a little bit how you write this search procedure. So what you see here at the bottom is a search procedure for the queens problem. Okay? And there are various things that you can see there. So the first instruction is a for instruction, and basically it's telling the system, iterate for every one of the queens. I want to assign a value to every queen. So I have to iterate over all the queens. The second instruction is actually pretty interesting. It's the trial instruction. And essentially that instruction is a non-deterministic instruction. It's not a loop. What it's trying to do is to assign a value to the particular variable. It's to choose a value in a non-deterministic fashion in this particular case. Okay? Now it's going to try to do that, find one particular value, but it's not going to try them all at this point. Okay? It's just going to pick up one, okay, in a non-deterministic fashion, and then execute whatever the body is below. Okay, but if later on, okay, the execution fail, okay, it's going to come back to this instruction and try another one. Okay, so a for loop is kind of iterating over all the values. A trial knows that it has many possibilities to actually do something, and it's going to pick up one. And if later on you are, basically in a failure mode, you're going to come back and try another one. Okay, that's a non-deterministic instruction. The last thing that you see in this thing is essentially as soon as you have a variable, you have selected a value for the variable, you are going to basically add a constraint to the constraint store, stating that that variable is basically assigned to that value. Okay, so that's 3 components that we'll see in a lot of the search procedures that we're going to see in this lecture. You start by iterating over the variable, you non-deterministic to choose a value for them, and you add the constraints inside the constraint store. Okay, remember the computational paradigm. Okay, so what you have is basically a constraint store that's pruning the search space, and then a search. Okay, what the search is doing is always adding constraint to the constraint store. Okay, the search is adding constraint to the constraint store, and the constraint store is basically sending a result back to the search, saying, okay, yeah, good, success, okay? Or sometimes you add a constraint and it says failure, okay, so no, you can't satisfy all these constraints. When something like that happens, you go back to a non-deterministic instruction and try another value for the variable, okay? So in a sense, what you need to do is that every time a constraint fails, okay, so you go back to a non-deterministic instruction and try a value which has not been tried again. Okay? If there is no possibility for that non-deterministic instruction, what you will do is go back to another one that was, the previous one, and try that and try another value for that non-deterministic instruction. Okay? I'm going to go into the details of this a little bit more, such that you see how basically the syntax corresponds to the semantics that I'm talking about. Okay? So when you look at a for instruction, essentially what you are doing, you can view that, you can unfold this loop, and what you're really doing is do a bunch of try instructions for the first variable, for the second variable, and so on. Okay? Now, if at any point you fail for one of these, you're going to go back to the previous one and try another value. If there are no values left, you're going to go back to the previous one, try another value, and so on. That's what the system is doing. It's basically, non-deterministically selecting some of these values. If at some point you fail, you go back to the previous one and try another value for that one. If there are no one left, you go back one more level up. Okay, and so it's essentially that's what the system is doing there. Okay, so for every queen there will be this non-deterministic instruction, and you are trying to see which values you can assign to that queen. Okay, now let's look a little bit into more detail on how the trial instruction is working. It's a non-deterministic instruction which can potentially explore all the values, but it only does so when basically activated because of a failure. Right? So in a sense, what you can view is this trial instruction is a big try instruction, okay? And which is basically telling you, oh, try first the value 1, the value 2, the value 3, and so on and so forth, okay? And in this particular case, if you fail for the value 1, okay, so if, for instance, the value 1, when you put it inside a constraint system, the constraint system is telling you, oh, I have a failure, you will go and move to the next instruction in the try, okay, and try the second value, and so on and so forth until you arrive at the bottom. If none of these values are actually successful, you will go back to a previous trial instruction and select the next try in the list where you had left out at the previous execution of that trial. Okay, so that's essentially what this try and for all, the way they are interacting and the way non-deterministic computation are basically computed. Okay, so what I want to talk about now are the various ways you can use this primitive to do various kinds of search. And I'm going to talk about variable value ordering, value variable labeling. Okay, I'm going to talk about domain splitting. I'm going to say how you can focus some of the search on the objective function. I'm going to talk about symmetry breaking during search, and then randomization and restart. Okay, in this lecture we'll do only the first one, which is basically variable and value labeling. We're also looking at the value of the objective function at the very end of the lecture. Okay, so variable value labeling are probably the most simple search procedure that you can design in a constraint programming system. It basically has two steps. The first one is you choose a variable that you want to assign, and then you choose a value. The first step you have to reiterate for all the variable. The second step is a non-deterministic step. Now, once again, you want to apply the first field principle, which means that you want to find the ordering of these variables in a very specific way. You want to start with the one which are the toughest to give a value to, and typically, the size of the domain of the variable is going to be a good indicator of what is tough and what is not tough. Okay, the variable which is the smallest domain means that you have removed a lot of value from that variable. It means that it's probably interacting with a lot of other constraints. It's probably a variable which is very difficult to instantiate. Okay, to give a value to. Okay, so the ordering that we will want in general is going to be dynamic. You just don't want to fix the ordering of this variable. You want to choose a variable which has the smallest domain, then you propagate all the constraints, that reduces the search space again, and then now you want to look for the next variable with the smallest domain. Okay, and that variable may not have been the second most attractive variable the first time around, because no, more values have been removed. Okay, so what you want to do is iterate this, choosing the variable with the smallest domain, propagating, choosing the variable with the smallest domain, propagating. Okay, And so this is essentially how you can do that in a constraint programming system. The for all instruction now is capturing an order. And in this particular case, what I do is that I look at the variable rho r, and I take the size of its domain. And that basically tells me what, at this particular point in time, the domain size of that variable is. Okay? So in a sense, you have to view this iteration now is look at all the variables, okay, which have not been given a value so far, take the one which has the smallest domain, and execute the body. Okay? So you take the variable which has the smallest domain now, you execute the body, so which basically will assign a non-deterministic will assign non-deterministically a value to that variable. Then you're going to go back to the loop and look at all the variables that you have not selected, at this point, and take the one which has the smallest domain now. Okay? Why am I saying no? Because essentially the constraint that we added started constraint propagation in the constraint engine, okay, in the constraint propagation part of the system, and has reduced the size of the domains. Okay? So basically what you have to see compared to what we have seen before, what we are doing now is choosing the order of variables that we're going to give value to in a dynamic fashion, taking the one which has the smallest domain at every time. Okay? So essentially what we have seen is that 2 steps. First step is choosing the variable, and typically the variable which has the smallest domain. That's the first field principle. Now at any point in time, you may have several variables which have the smallest domain. Which one do you choose? Okay? One of the good principles that you have to try that you can try to apply is choose the one which is the most constraint. Remember the graph coloring at the beginning, all the variables, all the countries have exactly the same color, possible colors. Okay? Which one did we choose? We chose a country which was connected to many other ones. It was very constrained. That's what we can do. Okay? Now in the particular case of the queens problem, for instance, we can choose the queens which has the smallest domain. And if they are ties, we can choose the one which is as close as the middle of the board as possible. Why? Because when you place the queens in the middle, it has a tendency to remove more values than when you place a queen on the sides of the chessboard. Okay? So how to do that? Well, essentially this is easy. You take the for all instruction that you have seen before, and now you are using a lexicographic criteria. You take the variable which has the smallest domain, and in case of ties, the one which is close to the middle of the chessboard. Okay? So essentially, same thing as before, except that now instead of choosing the value with one criterion, I'm basically using 2 criteria. Okay? One starting with the smallest domain, and then the variable which is the most constrained. Okay? Now remember also, one of the things that we had on the queens problem was this dual modeling, where you had variable associated with the column, and then variable associated with the row. Okay? Now, that's a good example to show how you can both choose a variable ordering in a dynamic fashion and a value ordering in a dynamic fashion. Okay? So what you see here, okay, is that we look at the row variables. That's the one that we want to assign. Okay? And we choose the one which has the smallest domain. And then we have to assign a value. Okay? And when we assign a value, essentially, this is equivalent is in giving a value to a column. So we can try the value in an ordering, which is also the first field principle, which says, oh, but choose the value which corresponds to the column variable, which has the smallest domain, because that column is tough to instantiate as well. And that's what you are doing here. Okay? You choose a dynamic order for the variables, then you choose a dynamic order for the values. In both cases, you are actually applying, the first field principle. Okay? So that's the kind of things that you can do in a constraint programming system. Choose a dynamic ordering for the variable. Choose a dynamic ordering for the values. Very interesting thing that you can do. Okay? So in general, okay, so when you have a variable value labeling, what you're going to do is to choose the most constrained variable, okay, first. That basically means the smallest domain or the variable that fails very often. Okay? That's the kind of things that you want to do. And the value ordering is going to be generally a little bit different. What you want to do is try to maximize the probability of finding a solution. So you're going to try to find a value which actually leave as many options as possible in the future. Okay? Because that helps you find a solution. You leave flexibility for the variables. So in a sense here, we are trying to look at the region which is the toughest, but also trying to find a feasible solution. Of course, sometimes this is just a heuristic. This is not, a rule that you have to apply generally. But this is typically something which is useful in practice in many applications. Okay? So essentially, what I've shown you so far is that in constraint programming, most of the time, okay, we try to use feasibility information for branching. And why? Because that's essentially what a constraint programming system is doing. It's basically reasoning about feasibility, pruning the search space. And that gives you a lot of information about which variables are tough, which variables are central to actually the problem we are trying to solve. But sometimes we have an optimization problem. And it's so we are trying to find an optimal solution for an objective function. And it's important to look at the value of the objective function as well. Okay? Now, as I told you before, when we solve optimization problem, that optimization function becomes a constraint every time you find a solution. So it reduces the search space. So the feasibility information is still very important. But we can do it better than just exploiting the feasibility information by also, reasoning about the objective function itself. And what I want to do now is illustrate that on a very interesting problem, which is generally very challenging for optimization system. And constraint programming is really nice for solving this problem. So it's called serializable data services, and it's essentially implementing protocol that gives you software which is reliable. Okay, so this is something that we did with some colleagues at UConn, and the protocol that we were trying to implement is called eventually serialized data services. And the way to think about this is that you have a set of components, okay, software components that you have to map on a set of machines, so a set of hardware. Okay, and to do that, you have to satisfy some reliability conditions. So there will be different components that have to be located on the same machine, some components that have to be located on different machines. But you want this protocol to be as efficient as possible. So you want basically to minimize the traffic, the communication traffic between these various components. If you place them on different machines, it's going to cost you more to actually exchange data between them. Okay, so when you formalize this problem, okay, in a mathematical programming sense, it becomes what is called a generalized quadratic assignment problem. So this is the data that you have. You have a communication frequency matrices, which tells you how much two components are interacting with each other. That's the data F. You have a matrix which tells you the distance between the various hardware components. This is a distance matrix H, okay? It's essentially the number of hops that you have to do from moving from one hardware to another one. Then the decision variables are going to be this vector x, and x is going to tell you for every component on which hardware that particular software component is going to be placed. And C is a set of components, and then you have two types of constraints. You have the collocation constraints and the separation constraints. The separation constraints are telling you that two components cannot be on the same machine. If they are, the protocol wouldn't be reliable. And then you have this collocation constraint just saying the opposite. These two things have to be on the same machine. And the objective function is going to be minimizing the traffic in the network. So you have the frequency matrix that you see there, and then you have the number of hops, and XA and XB are basically the decision variable. It's where do you place component A, where do you place component B? And what you're trying to do is to minimize the communication between all the components, okay? And that, of course, depends on how much they communicate and how far away from each other they are basically placed on the hardware. So this is the model, okay? This is the model that we have for this this generalized quadratic assignment problem. Okay, the model is essentially a straightforward implementation of what I just presented on the next slide. You see the objective function, which is a direct translation of the objective function that you saw on the previous slide. You see the matrix H there. It's a matrix indexed by two variables, so that's the element constraint that we saw a couple of lectures back. Then you see the two types of constraints, the collocation constraints, which are basically telling that two components which have to be collocated are assigned to the same component. And then for the separation constraints, what you have is basically all different constraints. What is really interesting in this particular example is the search procedure, because it's going to focus on the objective function. So this is what you do. At every step, until all the components have been placed, you will take a component I, which has not been assigned so far, and which is interacting with as many components as possible. It has a very high communication. It maximizes the communication with another component. Okay, so that's what you see there. Select I, which has the maximum frequency of communication with another component J. Why do you want to focus on that particular component? Because it's interacting heavily with somebody else, and therefore it will have a big effect on the objective function once you place it. Okay, and therefore that's why you want to focus on this one. You will gain a lot of information as soon as you place that component. Okay? The way you will place it is obviously by trying to make sure that you don't make this objective function increase too much. You basically want to find a value such that you minimize the communication, the number of hops with respect to the other components that it's interacting with. Okay? And that's what you see in this particular instruction. And then you assign the particular component to that particular location. So in a sense, what is important here is that you are using information on the objective function to drive the search. And this is a critical aspect on this problem. If you don't do that, essentially the execution time is going to increase by an order of magnitude. Okay? So let me try to summarize what we have seen in this lecture. What we have seen is one type of search procedure, which is very frequently used in practice. It's called variable labeling procedure. We saw the first fail principle, which tells you to try first when it's where it's hard, okay, where you are the most likely to fail. And that, first fail principle typically is using feasibility information, which variables have the smallest domain. But it can also use information from the objective function by looking at which components are difficult to place and would increase the objective function, which would make some of the other constraints much more difficult to satisfy. Okay? So we'll see more sophisticated search procedure during the next lecture, but this gives you a first taste on what you can do in a constraint programming system. Thank you.